Cannot one person do just copy 5
Okay,
times.
first one
Yeah, I think
is
heat. Maybe he know all cannot do
second one
already.
is 1 gram. So please listen.
Can if all cannot do then say bug.
An exam question is tougher than quiz. I tell you,
Can see okay.
much tougher than the quiz. So you have to understand. Okay? Yes. So you have to understand. This is very important. If you understand, you can answer very properly. I saw
No time.
5 or 6 students, maybe more than that. They answer very accurately.
No time.
Alright? Alright. Take a look. I try to explain the first law of thermodynamics and later I go to first law of thermodynamics. Okay, I try to explain in a very simple way. Okay, what is this? This one, any system. I can put any system, any system. Correct? It may be piston cylinder device or maybe rigid vessel. Anything. Okay? So this system, this indicates one system, right? This indicates system boundary. Alright, and this system possesses some energy, right? Every system possesses some energy. When the system is in stationary condition, it possesses internal energy. I can call it U. Agree, right? Okay, now I am going to apply heat to the system. I am going to apply heat to the system. What happens? You think first. Now I am going to apply heat to this system. What happens? This U becomes change, right? The red U becomes blue U, right? Correct. The amount of energy is changed. Or on the other hand, if I reject heat from the system, same thing happens. This U will be changed. Okay, I can write this red U becomes blue U, right? I call it U2. On the other hand, I call it U1. Alright. Then secondly, okay, I understand energy change. The shape of the boundary can be changed, right? Can be changed or cannot be changed. Right? If it is under rigid vessel, the boundary doesn't change. If it is on free system, right? The boundary will be changed. Correct. If I apply heat to the system, the boundary size will be increased, right? The fluid increases. Its volume, right? If I reject heat from the system, the shape decreases. Because total volume decreases. So now we understand, I apply heat to the system, you can see the volume increases, right? I can say this volume increases, right? Correct? So initially I can say, what is the volume? Total mass is M, right? I can say total mass is M. Total mass, specific volume initially V1. After applying heat, the volume becomes V2. Understand? This can change. And we can observe this thing easily. You can observe it. I apply heat to the system, the boundary change from V1 to V2, volume, mass is fixed, extensive property. And U1 becomes U2. Only these three things happens, right? Agree? Good. If the system is adiabatic, there is no heat loss, correct? If the system is not adiabatic, some heat is lost from the system, right? So how much heat is lost? We assume general case. So using the thin color, I show you some heat is lost. Right? Heat loss from the system to the surrounding. Heat loss, right? This thing may happen, right? If the system is adiabatic, there is no heat loss. I write it here, please note. For adiabatic system, there is no heat loss. Right? So heat loss I can say Q out from the system, right? So Q out is 0. For adiabatic system. Please note, otherwise you will be in trouble in the exam. Okay, so now what I can write? What is the input? Input is heat, right? And what is the output? Heat output. And energy change also output, right? Energy change. Because of heat, energy is changed. Plus this amount of energy, right? Plus the change in volume, right? Which is called boundary work. Then I can say how much volume is increased. This amount of volume is increased, right? How much? You can say this shaded area, right? I can say this is the shaded volume. Amount of volume is increased, right? Correct. So what we can see, observe. We can see Q, this one I can write Q in. So Q in becomes, I can write Q in becomes change in internal energy. U2 minus U1, right? Plus boundary work, right? The shaded volume. Correct. WB is shaded volume. I put here some shade. This volume, right, is work done. Alright? This volume times pressure is the work done, right? PdV. So this volume. Then I can tell you that what is the incremental volume? I can tell you dV. This amount of volume is increased, right? This amount is dV. If I do integration, then I can get the total work done. Right? So this one plus Q out. This is the energy balance. That means I can write, take a look, Q in equivalent to mass change in internal energy plus what is B? P d V, total volume, correct? Plus Q out. I just integrate this area. Then I take the total volume. Then pressure. This is the work done. Then I can write Q in MT U2 minus U1 plus, if I multiply with mass, M constant, P d specific volume plus Q out. Alright, this is the first law. Actually, if you write this way, it's enough. If you understand this concept, you can write them easily. Right? This is the heat input is equivalent to change in internal energy plus boundary work plus heat loss. If the system is adiabatic, this is 0. Correct? Then I can write this.
So QE is the work done.
Sorry?
QE is the work done.
Heat input. What done is this. PdV. Boundary work. Then you can see I can write Q in minus Q out is equivalent to MT U2 minus U1. This is actually WB, boundary work. This is actually WB. Then in your textbook it is written Q net minus W boundary work minus mt u2 minus u1. Correct. Q net becomes Q in minus Q out. This is the textbook equation. Q net minus WB mt u2 minus u1. That's all. This indicates the concept. If you understand this concept, then you can write this one easily, right? If you write this one, easy enough. Then you can solve the question easily.
So if there's no volume increase,
There is no volume. This is the rigid vessel, constant volume process. In that case, this is zero.
So there's no work done.
Exactly. Constant volume process, there is no work done because this is not increased, this is fixed. Correct. Then I come to some examples, then you understand. Alright. The question one, take a look. A piston cylinder device with a set of stops initially contains 0.3 kilogram of steam at 1 megapascal and 400 degrees Celsius as shown in this figure 1. The location of the stop corresponds to 60% of the initial volume. That means this indicates the stop part, right? This indicates the stop part. Right. When the piston comes here, for example, this volume indicates the 60% of initial volume. This is the concept. Now steam is cooled down. I am going to reject heat from the system. Determine the compression work if the final state is 0.1 megapascal and 50 degrees Celsius and 500 kilopascal, and also determine the temperature at the final state. Take a look. At state 1, you can see what is the state? This is state 1. I can say this is state 1. This is state 1. State 1 is defined by 1 megapascal and 400 degrees Celsius. I can write 1 megapascal and 400 degrees Celsius. This is state 1. And state 2. State 2 is 1 megapascal and 250 degrees Celsius. Alright. And state 3, only 500 kilopascal. Nothing is stored, only 500 kilos. So, I have to find the work done. This concept is work done concept. How to calculate work done. Please write down tutorial 5 question 1. Concept is how to calculate work done. How to calculate boundary work, WB. Okay, so now I go to, take a look, I show you the process. Compression work, what is the compression work? If the final state is 1 megapascal and 250 degrees Celsius, that means state 1 to state 2, right? What is the process? Constant pressure process, right? Constant pressure. 1 megapascal, 400 degrees Celsius, and 1 megapascal, 250 degrees Celsius. So same pressure. So 1 to 2 is constant pressure process. I can write this is constant pressure process. All right. Okay. Okay. At 1 megapascal, you have to go table A6. This is the pressure table, right? At 1 megapascal, you can calculate from table A5. You understand? From table A5, you can calculate saturation temperature. And this saturation temperature is smaller than the given temperature 400. So the state is superheated vapor phase. So state 1 is superheated vapor. Understand? Okay, what I can do, so what is the initial pressure? Initial pressure we say 100 megapascal or 1000 kilopascal. So I can say 1 megapascal, 1 MPa So this one I say pressure P1, right? I just draw a line here, dotted line. Right, this is dotted line. So I can write down constant pressure line, right? So this is constant temperature line, right? Constant pressure means constant temperature line. You have to draw. Right. Then we assume the state 1 is here, for example. So we can say the 400 degrees Celsius is somewhere here, right? Initial pressure, 400 degrees Celsius. So 400 degrees Celsius is here. So this one is temperature. I can say this indicates temperature T1, which is 400 degrees Celsius. Secondly, right, at pressure T1 and temperature T1, I can get specific volume 1000 kilopascal and 400 degrees Celsius, right? And you can see this is specific volume at state 1, which is 0.30661. Correct. Then I can calculate this indicates state 1. State 1 is this one. I can say this point is specific volume V1. Agree? Specific volume V1. No problem. Correct. This one number 0.30661 is this one. Now I am going to cooling down the system. Rejects energy from the system. It follows this way. Correct. And they say temperature is 250. Correct. And 250 degrees Celsius, you have to calculate what? Because you have to calculate the state is superheated vapor or here. So at this pressure, at P1, I need to know Vg. Correct. This Vg. This Vg I should know, this point. This Vg should be compared with this number, right? Then I say, oh, this is superheated vapor. Similarly, at 200 degree Celsius with 250 degrees Celsius, then I know V some number la. And this number should be compared with this number. If this point is higher than this, then superheated vapor. Otherwise, it is here. You have to compare. So now I can say state it is going cooling down, right? So I can say cooling process. Okay, I choose this is cooling process, right? So we can say at P2, take a look. Pressure 2 is 100 megapascal and 250 degrees Celsius. 100 megapascal and 250 degrees Celsius. This is this number, right? This is this number. So at 1 megapascal, what is specific volume? Saturated vapor, this point, right? And you have to compare Vg at 1 megapascal and this one. If this one is higher than Vg at 1 megapascal, then superheated vapor. Otherwise, it is here. Okay? But I didn't show you here because you know this. So here I found that I show you the condition. I found that V2, this is V2 actually, 0.23, right? This is V2. This V2 is higher than Vg with respect to 1 megapascal. Then superheated vapor. Otherwise, you cannot say. So this point we assume state 2. State 2 at 250 degrees Celsius. And 250 degrees Celsius, we assume this is here. Alright. So this temperature is 250. Okay? This is T2. This one is T2. It's 250 degrees Celsius. question. First question is, what is the compression what when the system changes from state 1 to state 2? Right? What is the compression? So at state 2, I can draw this line, right? Take a look. Can I draw this line? So this point is V2. Okay. So what is the compression one? I tell you, WB is equivalent to, should I write the equation? You remember WB is equivalent to MPdV, correct? Exactly correct. So this indicates the total mass. Pressure is constant. From 1 to 2, it goes a constant pressure process. Then I can write M and P constant. And what is the boundary? 1 to 2. Boundary is 1 to 2. Then I can write WB is equivalent to mass P constant 1 to 2. I do integration, right? Then I can write MP V2 minus V1, correct? What is P here? P here is P1. This is the pressure, right? And this pressure, P1. Alright, then I can write, what is the boundary one? Area under this curve. This area. This area is the boundary area, which is P1 times the distance from here to here. That's why I write MP V1 minus V2. Right? Then you should write V2 minus V1 because it is going this direction. And compression what? Answer is negative. So I correct this for you. Answer is negative. Negative answer because of compression. So MP, this should be V2 minus V1. This should be 2 and this should be 1. Right? And this one is going there and this one is going there. Alright? And what is the area under this curve? I can show you this area. Alright? Area under this graph is this point. Alright. Now you understand?
No.
Don't understand?
Practice.
Area under this curve. I tell you, this is the work done. Because the system goes from 1 to 2 at constant pressure. Right? Constant pressure. Then area under this graph, PV graph, is the work done. Actually, this is the area. Because mass is constant, right? This pressure times the difference between the volume. This is the area. Area of the rectangle. It looks like a rectangle. Alright? So this is question 1. And question 2, they tell you another story. Question 2 tell you it further cooling down, right? And goes to the stopper. When it goes to the stopper, it is coming here. After that, pressure drops from 1 to 2. Alright? So I am coming. May I go next?
We call V2 equals to VG as 9 minus.
V2 equivalent to?
VG 9 minus. It's the same value, 0.23.
This one and this one. No, different. This value is this one. 0.2375. And at this value is 0.30661.
The value of V2 is equal to VG.
V2 and V3 are same.
VG,
Cannot.
VG.
So shouldn't V2 be at the point?
No, I'm coming. No. V3 is here. It is going inside here. Because how you calculate the V3? 60% of V1. You multiply 60% times this. What is the number? You tell me number? Multiply. 0.6 times 0.30661. This is smaller than 0.23275. Right? Then it is here. Okay? Alright, I go to the next slide, then you understand better. You see, I have written here. V3, 60% of V1. Then 183. Alright? 183. Then I just draw, right? P1, P2, I think you understand. Alright? This one I say P1. So this is 400 degrees Celsius. Right, so this is state point 1. This is B1, correct? Then this is state 2. Right, this goes here. This is state 2. Then this temperature is 250, right? So I can say this becomes 2, and after that it goes to here 3. This one is V3, right? V3, and this one is 0.183966. Correct. Then they tell you after that the pressure drops from 1 megapascal, this is 1 megapascal, to 500 megapascal. 500 kilopascal. Pressure drop. That means from 3 to 4 pressure drop. 4, right? What is the work done? And here you can see this indicates the final saturation at state 4. This is T4, right? What is the T4? T4 becomes T saturation with respect to 500 kilopascal. Okay, and how you know this is in saturated liquid plus vapor mixture? At 500 kilopascal, you can calculate VF, you can calculate VG, right? Then you have to compare. This point V4 and V3 are same, right? Constant volume process because of the stopper. That's why we should drop. Then you can say, oh, this is liquid plus vapor mixture. Okay, I do an additional question for you. You calculate what is the quality at state 4. Additional question. You can write. Calculate.
Is this the assignment?
Quality at state 4. Okay. So what is the boundary one when the system goes from state 1 to state 4? Tell me. What is the boundary one? WB, right? From 1 to 4, correct? PDB. Then I can write mass is constant. 1 to 4, right? PDB. So area under this graph, correct? This one. V3 and V4 are same. Constant volume process. From, okay, I explain you again. I think you don't understand if I do this way. Okay, so WB, can I write this way? Mass, total mass, which is given, right? And I can write this way 1, 2, 3 P dV. Can I write?
Can.
Plus and 3 to 4 P dV. Correct. So 3 to 4, what is the number? This should be 0. Constant volume process. Then I can write WB mass and P becomes P1, right? This way. 1, 2, 3, P becomes P1. And V3 and V4 are same. MP V3 minus V1. Then you substitute the value, then you get the answer. Very simple. And what is the area? Area under this graph. Whole area. Alright? Then you substitute the value, then you get the answer. No problem. Okay, you can do it by yourself. An answer is given on the question. Alright? An additional question, calculate the quality at step 4. You can calculate, right? No problem. At 3 also you can calculate. No problem. At 500 kilopascal, I know VF, I know VG, I can calculate. At 1 megapascal, I can VF and VG, then I can calculate. No problem. Alright. Even though I give you the answer, I remove. So my answer is 30 minus 36 point, I give you the answer minus 36.79 kilojoule. This is the answer. Alright? Okay. Now determine the temperature at final state. What is the final state? Pressure is 500, temperature is this one. This is the final temperature. Final temperature is 151.83. We get it from the table. Because the state is in saturated liquid plus vapor mixture region. Alright? So I have also shown you at 500 kilopascal and V3 is this number, right? Vg is this value. 0.37483 is higher than 0.183966. So this is in liquid plus vapor mixture region. And what is the final temperature? Saturation temperature with respect to this pressure. Done. Alright. Then I go to second question. This question is a mass of 2.4 kilogram of air at 150 kilopascal and
familiar.
12 liters contained in a gas
Trigger.
frictionless piston cylinder device. Something like that. Take a look.
Something like that.
The piston cylinder device. This is the air. Mass of air initial is 2.4 kilogram. And what is the initial pressure? Initial pressure at 1 is, they say P1 is 150 kilopascal and temperature T1 is 12 plus 50 Kelvin, and the air is now compressed. Now I apply some force, correct? I do compression. Then the piston goes from 1 to 2. For example, the new position of the piston is here. I say 2. At position 2, they say the pressure becomes 600 kilopascal. Alright. And they also tell you during the process it is transferred from the air. That means they tell you, they also tell that heat is transferred from the air. It is lost from the air. And such that the temperature inside the cylinder remains constant. That means T2 and T1 are same. The temperature doesn't change. It is released from the system but temperature doesn't change. Okay. Then what is the process here? 1 to 2 is isothermal process or constant temperature process. Then I can say 1 to 2 is an isothermal process, right? Isothermal process. I can say now, okay, from basic rule, I know P1 V1 by T1 and P2 V2 by T2. I know, right? This equation is known to us. We know. Then I can write constant temperature process from 1 to 2. So that's why I can say T1 and T2, they are cancelled. So V1 by P1 V1 equivalent to P2 V2. Then I can write P1 by P2 V1 by V2. I can write it, right? So now they tell you calculate the work done. That means you have to calculate the boundary work. Okay, now additional question. How much heat is released from the system? Q is how much? Additional question is Q out is how much? You can calculate, right? It's very important. Understand the concept. Okay? Now I can tell you what is the work done for isothermal process. 1 to 2 is isothermal process. I can write this is the boundary work, right? PdV. I tell you previously. 1 to 2 is the boundary work. WB from 1 to 2. Then I can say what is P for ideal gas? PV equals to mRT, right? I can say PV equals to mRT. Then I substitute the value of P. So P becomes mRT by P. Then I substitute this value here, right? Correct. I substitute the value of P, which is mRT by V. So here at isothermal process, T is constant, right? The amount of mass is constant. R is constant. Then I can put mRT. Then I can say what I can write. I can write. Okay, one more step. I should do mRT 1 over V dV. After integration, you can write ln V, right? So V2 by V1. Final state minus initial state. So what is V2 minus V1? P1 minus P2 from the previous relationship, because V1 and V2 I do not know, right? But I can calculate anyway. So V2 by V1 is equivalent to P1 by P2. P1 I know, P2 I know, T I know, right? Then I can calculate the work done. Negative, right? Because of compression. Okay. Secondly, I give you extra question. How much it is lost? Tell me. It lost. Q becomes total mass, right? U2 minus U1, correct? Plus boundary work. Correct? Q net means Q out. Q, there is no Q in. So Q out. Correct? So I can write this is Q out. Q out becomes, this is negative, right? Becomes NCV, right? T2 minus T1 plus WV. So T2 and T1 are same, right? Right, it's cancelled. So this one is 0. So Q out becomes WB. So what is the WB? 272 kilojoule. Alright? So this is the tricky part. Okay? U becomes CVT. H becomes CPT. I think, have you gone through the Lamb's lecture? Wow, that's why. Oh. This one, I think another lecturer, Prokon Fei, tell about it. Okay, even though I write for you. Okay. CPT equivalent to H. Is equivalent to H. And U becomes CVT. Two equations. Internal energy is CVT, enthalpy is CPT. And another equation is Cp minus Cv is equivalent to R. This is true for ideal gas. All these are valid for ideal gas only. All these. For ideal gas, not for real gas, okay? Okay? All these are valid for ideal gas only. Okay? For real gas is different. For ideal gas, U is a function of temperature only. H is a function of temperature only. Okay? So Cp minus Cv is equivalent to gas constant. R. You should know this, okay? Try to memorize these three. Don't forget. Alright, so I go to the last question. In this question, I go very fast this one, don't worry. Okay. This question, can you stay half an hour? Okay. Figure 1 shows, figure 1 shows piston cylinder spring arrangement. The system contains initial volume, I can write, initial volume V1 contains 2.5 times 10 power minus 3 meter cube of liquid water vapor. Okay, with the quality of 20%. That means X is 0.2 quality. Okay, fine. Initial state I know. At the position shown, the piston is free to move. The piston weighs 150 Newton and has a cross-sectional area of 50 centimeters square. That means 50 times 10 power minus 4 meters square. Alright. The system is exposed to the atmospheric pressure of 95 kilopascal. That means atmospheric pressure is given 95 kilopascal. The atmospheric pressure, right? And the system is now brought in thermal contact with the heat source of Q. The heat transfer from the reservoir causes the final pressure of the fluid. Take a look, 500 kilopascal. That means when you apply heat to the system, the piston moves from state 1 to state 2, right? So I can write down this is state 1. So state 2 becomes here, right? When the piston touch the spring, this is state 2. Correct? And after, okay, when the pressure goes from 1 to 2, this is constant pressure process, right?
Yeah.
Constant pressure process. So I can write down P2 becomes P1. Good. Say after that, what happens? The spring is compressed. We assume it travels this amount of distance, which is delta L. I have to find this distance. Alright? At state 3,
Another question like that also.
pressure at that point is 500 kilopascal. Is given to me. Okay, now the question is, calculate the initial temperature and total mass of the fluid. That means I need to find the initial pressure. How? Mass of the piston plus atmospheric pressure. Then I know initial pressure. When I know initial pressure, I can calculate initial temperature because state is liquid plus vapor. Done, right? And I can calculate its, okay, what is the second question? Calculate the quality of water vapor when the piston touch the spring. Right? So at that point, I can calculate V1. How? Why? At initial pressure P1, I have to calculate first. Then I can calculate Vf and Vg. And quality I know. Then I can easily calculate specific volume at step 1. Done, right? Then total volume is given. So total volume by specific volume, I can calculate the mass. So first question is solved. Done. What is the second question? From here to here, it goes here. When it goes here, then volume increase or decrease? Increase, right? How much? This one plus area of the piston times this distance. I know the total volume. So total volume divided by mass. I know the specific volume. Correct. And what is the pressure here? Same initial pressure. Right. Then I calculate V2, compare V2 with Vf and Vg at initial pressure. Then I select this is superheated vapor or liquid plus vapor mixture. If it is liquid vapor mixture, I can calculate the quality easily, right? Done. Then after that, I have to calculate this number, delta L, because I know the spring constant. Then I can calculate delta L. When I know delta L, I can calculate V3, right? Total V3. The total V3 by mass, I can calculate specific volume. At state 3, I know pressure P3, 500 and P3. Then everything is done. And question is solved. Sorry? I'm coming. D is first law. C is area under the PV diagram. Is all done. All right. Okay. The first question. Take a look. Calculate the initial temperature and total mass of the fluid. Initial volume is given. Take a look. Initial volume is given. Is given data. Quality is given. Area of piston is given. Atmospheric pressure is given. Right? Is given data. So you have to do the force balance. This is the working. Force balance tells me P1 becomes atmospheric pressure plus weight mg. Okay? This one I know. So this value is equivalent to 125. P1 is 125 kPa. At 125 kPa, I can calculate initial temperature. I can calculate Vf. I can calculate Vg. You understand? Please listen, otherwise your exam will be dying. I tell you. At 125 kPa, you calculate T. You calculate Vf and Vg.
Okay.
Right? Then you can calculate V1. Because I know Vf, I know X is given, and Vg, Vf I know, I can calculate V1. Alright? So what is the total mass? Total mass is equivalent to I know V1. V1 you can calculate this number. Okay, so now you can calculate M. Total mass MT equivalent to total volume V1 by specific volume V1. Then you get it. Alright. I hope that you understand this. Now, total mass, I'll show you everything. M is 9.064 10 power 3. So what is initial temperature? T saturation with respect to 125, 105.97. So this is the initial internal energy at initial condition, because I am going to find Q. So that's why I need to find Q1. UF plus X times UFG. I can get it. Okay? So this is very important. Q. That's why. Number B, calculate the quality of water. So I can calculate V2, specific volume, V1 plus this distance. Because the piston goes here. This is state 2. Then this is V1 and this one incremental volume, right? Then I can find final volume at state 2. Then specific volume at state 2, V2 by total mass. Then I can calculate V2. Then I calculate the quality, which is 0.28. Because all these you know how to calculate, nothing new. Right? If you do not calculate this, you please go to tutorial 2 and tutorial 3 again.
Okay.
Okay? I hope that you know this. Very straightforward. Then calculate the work done by the gas and the spring. How you can calculate?
Area under the ground.
Yes.
Wow.
How? Because at that point I know, right? This is state 2, this is state 1, right? And at that point, this is state 3. And it travels the distance, we assume this is delta L. Take a look. From here to here, delta L. And you have to calculate the value of delta L. Can you?
Yes.
Good. And what is P3?
3.
P3 is 500, right? I can calculate what is delta P. Delta P becomes spring force by area of piston. Right. What is spring force? Spring force is K times delta L. Today you have done this already in the exam also. Right. What is delta P?
You do this there, is it?
P2 minus P1. P2 minus P1 becomes 500 minus 125. P2 minus P1 is equivalent to, what is K? K is 7.5, right? Delta L is given. What is the area of piston? 50 centimeter square. 50 times 10 power minus 4. Then I can find delta L. Delta L I get here 0.25. Okay? Today delta L is 0.05, right?
Yes. Wow. Really what?
Who gets 0.05 today? Today delta L is 0.05.
Yes.
the link
Cool.
Okay.
I forget that.
I get 0.02.
Okay. Now you take a look at 500 kilopascal. This is 500 kilopascal, right? Okay.
Ask Ethan what you get.
Apple.
You know when you get 30k?
This is 500 kilopascal.
30k.
Okay. What is specific volume V3? Tell me.
30k Pascal.
V3 becomes, what is
Yeah lah,
V3?
350 total.
V2 plus
3
delta L
Oh, my
times
delta.
area of piston, right?
Delta is
Then I
the
get
part.
Oh.
V3 4.75 times 10 power minus 3.
So today the delta P is 30 kilopascal.
30, correct. Then specific volume I can write V3 total volume by mass. Then after that I get 0.524. Alright? Okay. At 500 kilopascal, take a look. What is Vg? Vg is this one, right? So I can say V3 is higher than Vg at 500 kilopascal. What is the state? State is superheated vapor. State is superheated vapor, right? State 3 is superheated vapor. State 3 is superheated vapor. Correct. Done. So you can calculate T3 and U3 from the superheated table. No problem. What is the superheated table? I have to look for 500 kilopascal and this number. Okay, remember the specific volume now is 0.53524 meter cube per kilo. Okay? So now I am going to the next slide. Sorry?
Go back for 1 second.
Go back.
Difficult to
Demoralized.
wait.
Eating my friend.
Alright.
Yeah. Really, man? I see 0.
Okay.
Pause.
Thank you.
Alright, from there I know. V3 I know, everything I know, right? Now I can calculate the work done. Now you see how to calculate the work done. This is very important. And this is the foundation of calculating work done. For a complex system. Take a look. Right. What is the initial pressure? Tell me. 125, right? 125 kilopascal. This is P1, which is 125 kilopascal. What is the final pressure? 500 kilopascal. Yeah, 500 kilopascal I can write here. This is P2 or P3, right? 500 kilopascal. Right. Now you can tell me what is this? Temperature T1 with respect to 100 and this is temperature T1. Nothing new, right? T1 becomes T saturation with respect to 125 kilopascal. Right? And initially, what is the quality? Quality is 20%, somewhere here. So this one is specific volume V1, state 1, right? How the piston goes? Goes from constant volume process, right?
Yeah.
From 1 to 2. From 1 to 2, constant volume process. We do believe this is here with 28%. This is V2. And V3 is superheated vapor. That means V3, it goes this direction. Compression, right? Spring compression. Same as today's exam paper. Nothing new. This is V3. Correct. So now, and T3 you can find from here, right? And this one is temperature 2, and this one is another temperature. And you believe this is somewhere here. This is temperature T3.
Oh.
Right, done. So now they tell you what is the work done. Tell me what is the work done. This area, right? this area, correct? This area. So I can write, I forget this equation, you can do by yourself. So WB becomes mass, this area, N times P1 times V2 minus V1, correct? Plus area of the trapezium, this area. Correct? Area of the trapezium. I don't use this equation. I use my one, right? Half times m. What is the trapezium equation? M times P3 plus P1, right? Times V3 minus V2. Right, done. But here we write another way. We write first this rectangle, then this triangle. Same thing. In this, here I show you, first is the rectangle from here to here, plus the triangle. Same thing, no difference. So, and you get the answer here, which is, I got the answer here, take a look. You do calculation by yourself, and I get the answer 0.5155 kilojoule, right? Work done by the gas. This is work done by the gas. This is work done by gas. And work done by the spring. Work done by the spring is equivalent to area of the triangle. Remember, only area of the triangle is the spring area. Right? And I do believe you go to the Lamb's lecture and take a look. This area of the triangle, okay? This indicates the spring area, which is half times m P3 minus P1 times P3 minus P2. And I get the answer here 0.23436 kilojoules. Alright, you take the load rate.
Okay, next question.
You go to the labs how to calculate. Okay? If I say I need another half an hour.
Yes, next question.
Okay? And all of you become tired. Maybe next class I will tell you how.
This class.
Okay. So this one the assignment.
Haven't finished. One more. Calculate the heat, Q. So U1 you calculate before, right? Now U3 we can calculate with respect to this pressure and specific volume 0.524, right? 524 is found between here. Okay? Then I can find U3 here. This is U3. Then you can calculate this one. Then finally you can write, you remember, right? Q becomes Q in. This becomes, what is the equation? Tell me. Q in becomes M U3 minus U1 plus boundary work. Done. Okay? And boundary work we calculate before. And what is the, and you substitute the value, then you can find the answer. You do by yourself. And another question, calculate final temperature. Final temperature, T3. So T3 you have to do interpolation between Here, right?
Yeah.
Then you can find
T3.
T3. And Q in answer is 18 point. I give you the answer.
不用看 subscribe
18.17 kilojoule. I get the answer.
What is T3?
And T3 I get here. You can do the interpolation. T3 minus 300, right? Should I write?
Yeah.
350 minus 300. 0.524 minus 0.52261.
0.5715.对啊，很恶心啊！
Done. So you know the calculation is not very easy. You have to
Yeah,
Then
the
the
number
250 kilopascal.
Same thing.
don't like that. You should give more time.
The
Yeah,
number.
You know, in the exam hall they give you how many 4 questions they give you.
I don't want to
2.5
know.
hours.
1A 2A 3A 4A 5
I give you 1
Two
question.
questions. You 2 questions 45 minutes. Cannot. 4 questions.
yeah
Oh, the small question.
4 is the same one.
last week was
Eh, market ah, market. Okay,
1A 1B 1C 1B 1E
还价还价。
then I read myself.